So in this series of videos we're going to talk about optical instruments, and about the simplest optical instrument there is a simple magnifying glass. And the first scientific use of a magnifying glass was documented in the mid-13th century, so the mid-1200s, by the English philosopher Roger Bacon. Now, the magnifying glass that I've got here, and a typical magnifying glass, is just a simple converging lens. And if we draw the ray diagram for how this magnifying glass works, as we can see here, it produces a virtual image of an object that's placed in front of the lens. Now, if we look at that virtual image, we can see that it is indeed larger than the object, and so we might conclude from that 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 is how a magnifying glass works. It creates a larger image. However, if you look at that picture, the image is further from the lens. And that's a problem, because if I hold my hand out here, so it's a lot closer to the camera, my hand now looks quite large. If I move my hand back, it now looks quite a bit smaller. So objects that are further away appear smaller, and in fact the size of an object observed by our eyes depends on the angle that it subtends. So essentially the difference in angle between the top of the object and the bottom of the object. So when we look at our diagram for our simple converging lens, what we see is that the object is closer to the lens and it's smaller. The image is a lot larger, but it's also further away than the object, and so actually the angle that both the image and the object create for an observer sitting the other side of the lens is exactly the same. So in that case, how does a magnifying glass actually work? Well, to understand that, what we're going to have to do is look at how we use a magnifying glass. So if I take my hand and I hold it out here, I can focus on it at a distance of about 25 centimeters. So without my glasses, because I'm short-sighted, I can actually focus a lot closer than 25 centimeters. But with my glasses on, I can comfortably focus at about a distance like this, which is 20-25 centimeters. It varies from one person to the next. However, if I put a magnifying glass in the way, then I can move my hand quite a lot closer, and I can now focus on my hand at a distance that's a lot less than I can without the magnifying glass. And that is actually how a magnifying glass works. It allows us to place objects far, far closer to our eyes than we can without the magnifying glass. It's also the reason why a magnifying glass like this, apart from being sold to kids as a sort of toy or investigative tool, it's also sold to older people, because as you get older, the near point, this near point that we discussed, recedes and gets further and further away. And so older people tend to end up buying reading glasses, and reading glasses are essentially just a converging lens like this, and the reason for that is that it allows them to focus closer, and so it moves the near point of their vision from beyond where you can comfortably hold a book into a range where you can comfortably hold a book, and so that they can then focus on a book held at arm's length without the problems that you have with the near point being further away than the length of your arms. Okay, so this is how a magnifying glass works. It allows us to focus on things nearer than we can otherwise focus. So let's have a look at the mathematics and the descriptions behind that, and to do that we're going to have to look at ray diagrams. We're going to have to define what we mean by angular magnification, and then we're going to compare the two cases, one without a magnifying glass to one with a magnifying glass, so we can actually measure the magnification power of a simple magnifying glass like this. So here's the situation that we've got when we're comparing what's going on first with the naked eye and then with the magnifying glass. So in the first instance with the naked eye, what happens here is our observer here, represented by this eyeball, will place an object as close as they can to their eye and still focus on it. And so this distance here, this is called the near point of vision. So this is the shortest distance at which you can focus on an object using your eyes. Now what happens with a magnifying glass is that when you're looking through the lens of the magnifying glass, you aren't focusing on the object here, you are instead focusing on the image that the lens has created, which is here. And so what you can see here is that now the object can be a lot closer to your eye than the image, because it's the image that you are going to focus on, right? You're no longer trying to focus on the object, you're trying to focus on the image, and so the object can be a lot closer to your eye than the case with the naked eye over here, because the magnifying glass allows you to, it creates an image, and then it's the image that your eye is focusing on, not the object itself. So in order to define the magnification factor here, it's not going to be helpful to compare the heights of these objects, because we haven't just got a height involved, we've also got a distance away from the eye. In this case, the object is a distance d away. In this case, the object is a distance u away, and in fact we're focusing on the image, which is a distance v away. So the first thing we need to do is we need to define what we call the angular magnification. And so the angular magnification is going to be the angle that we subtend in the magnified case. So this is going to be theta prime. And it's going to be that divided by the angle that is subtended by the object in the non-magnified or the naked eye case, where the angle is just theta. So the angular magnification is defined as the ratio of these two angles, just like linear magnification. If you remember, linear magnification was defined as the height of the image divided by the height of the object. So it's the same sort of ratio, only now it's an angular magnification and a ratio of two angles as opposed to a linear magnification. So here are the two diagrams we've got, and so what we need to do now is come up with a way of calculating those two angles, theta and theta prime. Okay, so here we have the two diagrams again, and what we're going to do now is we're going to do a little bit of maths. So what we're wanting to find, remember, is the angular magnification, which is theta prime divided by theta. So this is as near as you can put the object to your eye, which means that this distance here, d, is the near point of vision. So this is the closest at which you can focus, which for a human is about 25 centimeters, give or take something. So this is our naked eye, this is our magnifying glass, we've got an angle here theta prime, we've got an angle here theta, and what we need to do now to find the magnification is find values for these two angles. So to do that we're going to use this right angle triangle here, and we can say that the tangent of theta here is going to be equal to the opposite, so that's O, the height of the object, divided by D, which is the near point in vision, because this is as large as you can make the object without a magnifying glass. Now, since we're typically looking at small objects, we're going to make the approximation that theta here is small, and so that means that for small angles, we've got this standard small angle approximation that the tangent of theta is approximately equal to theta if theta is small, and so we're going to use this approximation here. So this is our case for the naked eye. For the magnifying glass now, if we come over here, we've got the same right angle triangle here, and so we're going to use this right angle triangle for the tangent of theta prime, and this is equal to the height of the object divided by the distance along here, which is u, the distance of the object from the lens. And again, we're making the approximation that this is a small angle, so this is approximately equal to theta prime itself. And now we go back to our magnification factor. Well, we've got an expression for theta prime, we've got an expression for theta, so let's put them in here. So theta prime is O divided by U, and then we're multiplying it by 1 over theta. So we multiply it by 1 over theta, which is multiplied it by D over O, and we can see that the height of the object nicely cancels out, and we're left with D divided by U. Now, this is our magnification factor. D is nicely defined. It's the near point of vision. U, however, isn't. It's just the distance between the object and the lens. So the question now is, well, how do we determine what the value of that is? Well, what we first need to do is we need to write down the lens equation for our magnifying glass case. So 1 over U plus 1 over V is equal to 1 over F. And so if we rearrange this, we want 1 over U is equal to, and so we've got 1 over F, but for V, remember, V is going to be negative when we put it into the lens equation because this is a virtual image. So normally I would write 1 over minus 1 over V here, but because I know that V is going to be negative, and what we're interested in here is the distance that we're holding it away, we're not interested in whether it's a positive or a negative distance when we put it into the lens equation conventions. All we want is the magnitude of the distance. So I'm going to put a plus here, and then I'm going to put a magnitude around V. So what it means is that we are adding to 1 over F here, we're adding 1 over V, where V now, or modulus of V, is just the linear distance that you'd measure on a ruler, and we've coded in the fact that we know this is negative simply because this is a virtual image. So when we do that, if we have a look at our magnification factor, then we want the maximum magnification. Well, the maximum magnification is going to occur when 1 over U is as large as possible. So here's 1 over U, and 1 over U is 1 over F. Well, that is fixed by the focal length of the lens, and so that is determined. We want the maximum magnification for this lens, so that isn't a variable. We can't change it because then, of course, we'd have a different lens. So we want the maximum magnification for this particular lens, so there's nothing we can do with the focal length here. But we can control V. So we want 1 over the modulus of V, where V now is just the distance here. We've coded in the fact that we know it's negative because this here is a virtual image. We want 1 over V to be as large as possible, and we get that by making V as small as possible. So how small can we make V? Well, remember, we've got this eyeball here that's looking at it, and the eyeball has to be able to focus on the image. So that means that the image cannot be nearer than the near point of vision. So that means in the limit that V gets as small as possible, V is going to be equal to D, the near point of the human eye. And so that's how we can determine what the value of U is. 1 over U, it is simply equal to 1 over F plus 1 over D. And that gives us our value for U. So let's put this together and come up with an expression for the maximum magnification. So here's where we were at the end of the last slide. We've got an expression for our angular magnification that was D over U. We had an expression for 1 over U from the lens equation, remembering, of course, that V was a negative distance in the lens equation that we took account of by putting a modulus in here, so we're just looking at the distance and flipping the sign to plus. And we saw that to get the maximum magnification, we needed 1 over U to be the maximum possible value, and that was when V is as small as possible, and that's when the image is at the near point of human vision. So if we combine these two together, then we end up with the maximum magnification here being equal to, well, it's going to be D times 1 over U, so it's D times 1 over F plus 1 over D, and so that gives us our maximum magnification that is just simply D over F plus 1. And so that is the maximum magnification that you can get from a magnifying glass, and it depends on the value here of the near point of vision. So that's our maximum magnification. Well, what about our minimum magnification? Well, so if we want to get our minimum magnification, then we want 1 over U to be a minimum, and so that is going to be where we have 1 over F plus 1 over, and then again it's the modulus of v, but we want the maximum value now for v. So what is the maximum value for v? Well, let's have a look and see what happens when we place the object at the focal point of the lens. So here's a diagram about what happens when we place the object at the focal point of our magnifying glass. Now if we look at this triangle here, and we look at this triangle here, we can see that these are exactly the same triangle. They've got the same length because this is, the bottom side is the focal length f. The height of the triangle is just the height of the object, so these sides are the same, and so we know that they're both right angles, so these are identical triangles. So what that means is that these two rays are parallel. And where do parallel lines converge? Well, parallel lines converge at infinity. So what this tells us is our image is an infinite distance this way. So what we find is that our magnitude for V maximum is going towards infinity, which means that 1 over V, when it's at its maximum, is equal to 0. And so that gives us that 1 over u is just equal to 1 over f, because 1 over v in this case becomes 0. So if we put that into our magnification factor, so this is now going to be our minimum magnification because we've made v as large as we can get it, right? You can't get bigger than infinity. So our minimum magnification now is just going to be d divided by f. So this is the least magnification you can get out of your magnifying glass, and you get it by then holding the lens so that the object is at the focal point, and that generates an image at infinity. So why would anybody do this? Well, the problem with getting the maximum magnification is you have to have your eyeball right up next to the lens here, which means that you're the only person that can see the image through the lens. And so this is sort of the Sherlock Holmes type mode of operation where you've got your magnifying glass up to your head. However, if you want to share what you're seeing with other people, then our eyes are really good at focusing on images that are at infinity. And so if you set it up in this way here, then lots of people gathered around can be focused on it at a distance, and you can have lots of people look at the image, and so you can show the same image to lots of different people, but the price you pay is that you lose this extra +1 in the magnification power. So usually it's not a huge effect, but it is an effect, and you do get a slightly smaller magnification factor. So now we've seen how to calculate the magnification power of a simple magnifying glass like this, both in the maximum Sherlock Holmes case where you hold it up to your eye and you bring the object into focus, or in the case where you get the minimum magnification where you hold it close to the object and you get the image produced at infinity, so lots of people can see it, not just the one person holding the magnifying glass. Now, a magnification factor of these magnifying glasses is rather limited. This is a cheap one that I got off Amazon for about $12, and you can't achieve the maximum magnification with it because as you get close to that maximum magnification factor, you start to get a lot of these aberrations, the spherical aberrations, because this is quite a large lens. It's also relatively thick, and so this maximum magnification power is quoted as ×8. You can't get it because of the distortions caused by the lens as you get close to that maximum magnification. And this in fact was a limitation of magnifying glasses, and so for centuries they were limited to no more than about a factor of 2 or 3 or even 4 in magnification power. Also, of course, because something as simple as this would have been a technological marvel even as much as about 400 years ago, because they had no way to make a lens that was as large and as clear as this one. So about the end of the 1500s, early 1600s though, we had a revolution, and that revolution was the invention of 2 optical instruments, the telescope and the microscope, which were created by combining lenses together so that the limitations of a single lens could be overcome. And the impact that those two simple inventions had on our understanding of the universe cannot be overstated. It was an incredible impact, both by looking at the small scale and looking out at the heavens with the telescope. And those two simple optical instruments are what we're going to talk about in the next two videos.